We gotta learn first. Okay, we'll talk about that when we get to calculator time.
My paper got bent. Pretty. Are you doing a piece of paper?
Do you want to take notes? Okay, so we're going to start talking about the 10 basic functions. And these are 10 basic functions that are used in mathematics all the time. And so they're ones that you should be familiar with their graphs, and then you should be familiar also with their equations. And a lot of what we do will involve manipulating these basic functions in some way, making them more complicated, or using them to solve complex problems. Okay? So what is the most basic, easiest function of all? Y equals x. It doesn't get any easier than that. Y equals x. And so if you, oh, I gotta remember. If you were to graph the function y equals x, what would it look like?
It would just look
yeah, it's a diagonal 45-degree angle line that goes straight both directions. And so what I mean by, that's the basic function is that all of the other linear functions that you've ever studied or worked with in your whole life are all based on this. Remember when we talked about transformations? You can move things up or down, stuff like that. So if I, instead of y equals x, if I graph y equals x plus 3, what would that do to the graph? It would move it up 3. So it would be the same graph, just shifted. And then if I put like a 2 in front of the x, what would that do? If I put a 2 in front of the x. It changes the slope. You guys have learned all of slope, but what did that do when we talked about transformations when you put a number in front of the variable? We talked about what? Right, we talked about vertical stretches. Okay, so that would stretch that by a factor of 2. So what's that? No, the 2 in front of the x. Okay, so anyway, my point is all of the linear functions that you ever work with start with the basic equation y equals x. Okay, so that's an easy one. You should all know that. And then it says in your book, this is also called the identity function. Interesting fact, this is the only function that acts on every real number by leaving it alone. Not very interesting, really. Okay, next one. Another basic function. It'd be better if you didn't have your book open. You could just like think about it. Y equals x squared. Did you cheat? Okay, so we had y equals x. Another one that we work with all the time is y equals x squared. And you all know what that looks like, right? What does it look like? I heard it. It is a parabola.
Parabola.
I feel like this class has all of the kids that we wanted from last year.
It totally does.
Because like I thought I heard Lane Bruner's voice and I was like, yes, he's not in. Okay, y equals x squared. Parabola, same thing. We could take that graph and we could stretch it or shrink it or move it up or move it to the left or whatever. And any quadratic function is based on this guy right here. Here's your interesting fact about that. The graph of this function called the parabola has a reflection property that is useful in making flashlights and satellite dishes. Any idea what that's all about? We'll talk about in May. Seems like a long time away now, but it will come. We'll talk about these in sort of a different way. Parabolas have a thing called a focus that the graph is based off of. And the property that they're talking about is if this is a lens of a flashlight and this is the light bulb, the rays of light go out from the bulb, right?
Oh, nice.
And a parabola has a property that anything that hits it from this focus point leaves, they all leave parallel to each other.
That's pretty
Okay?
cool.
And so that's why your flashlight beam is focused instead of, you know, kind of spread out all over everywhere. And then the same is true with the satellite dish, but opposite, the little, you know, thingy in the satellite dish, whatever that little,
Yeah.
I don't know what that thing's called. You know what I'm
Ball
talking
in the
about?
middle.
Yeah, a little ball in the middle, yeah. The signals come into the satellite dish, and no matter where they come in, they bounce off of the parabolic dish and then into that little ball in the middle, which then magically turns it into a football game. I don't know. Okay?
That's actually a cool fact.
It's an interesting fact. Pay attention.
Wait, quick question. I don't know if there's anything.
Okay, good then. Go ahead and ask it.
Do your seniors get out early this year, or did they take that rule out?
Oh yeah, there was that early last year. I assume you get out early. You can't have graduation after school that early.
That's not real.
Are you seeing them?
I don't know. I just show up.
Good call. That'll get you far. I've been doing that for 24 years. Worked pretty good
Look at
for
you
me.
now.
Yeah. Look at me now. Okay, next one. What's another? Oh, come on. We did y equals x, y equals x squared, y
X
equals
cubed.
x cubed. Another one.
Oh, gee, that's
Okay. And so this is also, now we're getting into maybe a little bit of shaky territory for some of you, but you should be able to conjure up this graph right off the top of your head. It's like a parabola cut in half and then twisted. Okay, a little y equals x cubed action going there.
What's interesting about this?
What's interesting about the y equals x cubed graph is that the origin is called a point of inflection, okay? Which means that it's a big calculus concept. If you take any point right there and send it through there and go the same distance through, it'll be back on the original.
I'm interested.
It's not that. I didn't write the book.
I guess I figured that out.
Yeah. Okay, so that's all for the powers. We don't get into x to the fourth, x to the fifth, and so forth. You don't really use those very much, although they do come up every once in a while. So what did you say one? Somebody said one. Okay, y equals absolute value of x is another one. You know what we should have done is made like a Family Feud game out of this. 100-student survey, top 10 answers on the board. Name a basic function.
There's never been top 10.
Oh my gosh, I love that.
Is there been a top
They do
10?
top 8.
The top 8
They
is the
don't do
most.
top.
I said 6, you said 10. Guess you're
I'm
wrong.
still wrong, is the point, right?
Yeah.
Okay.
I was gonna say we both win.
Okay, y equals absolute value of x, what does that look like? Yep, that's the old V-shaped graph, like this, and like this. So the reason I'm putting these up there here and then you're putting them in your notes is because you should be able to, just like, when I say the graph, I mean the function, you were able to picture the graph. Or if I give you the graph, you know what function it came from, that's what we're working towards. Okay? Not a very interesting fact, but their interesting fact is this function has an abrupt change of direction, a corner at the origin, while our other functions are all smooth. That's obvious. Actually, that does come into play quite a bit in calculus. You will be someday.
I hope not.
College. Okay, what was that? 4 of them?
Yeah.
Okay, got 6 more.
Y equals 1
What?
over x.
The sine function, very nice. We got into sine and cosine last year, did we not?
Nope. Yeah.
Yes.
So what you should know about the sine function is it is the one that starts at the origin. And how long does it take for it to complete one up and then down? Anybody know?
2 pi.
2 pi, yeah, 1 cycle. This is pi right here. This is 2 pi right there. How high and low does it go?
1.
1 and negative 1. Okay? And of course it's on the other side also, but we usually only mess with the positive side. Alright?
Yes, can we do?
Yeah, if we did sine, we might as well do cosine. That would be our next winner. What is different about the cosine function compared to the sine function, or I should say graph? How do they differ, or how are they the same?
Hey, 1 second.
Right, cosine starts up here at 1, and then goes down right away and then comes back up. So sine starts at the origin, that's important. Cosine starts at 1. Okay, I don't know how you remember that. They both bounce between 1 and -1. And they both take 2 pi to complete 1 second. All right? Okay, how many is that? 6? What else? Elliot, you cheated and said 1 for the book. 1 over x.
What is that?
Yeah, 1 over x is a funky one. It looks like this. Oh, I forgot to tell you your interesting facts about sine and cosine. So your interesting fact about sine, it says this function and the sinus cavities in your head derive their names from a common root, the Latin word for bay. Bay, B-A-Y. This is due to a 12th century mistake made by Robert of Chester, who translated a word incorrectly from an Arabic manuscript. We do what? We can do x over 1. We already did. Interesting fact about the cosine function. Local extrema of the cosine function occur exactly at the zeros of the sine function. Okay, so this is what the 1 over x graph looks like. Did we did these, yes, a little bit? And moved them around and found the asymptotes and stuff, right? It was terrible. Okay, this curve called a hyperbola also has a reflection property that is useful in satellite dishes. So maybe I lied. Maybe the flashlights are parabolas and the satellite dishes are hyperbolas, but you get it. It's the same idea. All right, 3 more. They're kind of weird ones. So I will just give them to you. Yep, one of them is the square root of x. This is going to be number 8. Really?
I'll get it for you if you like. Okay.
0, 0, because the square root of 0 is 0. Then we got 1, 1, and then the next easy point would be what? 4, 2, because the square root of 4 is 2. And then we have to go all the way out to, you got something against 9. Square root of 9 is 3. So it starts to flatten out quite a bit as it goes. Okay, here's your interesting fact about the square root. Put any positive number into your calculator, take the square root, then take the square root again, then take the square root again, and so on. Eventually you will always get to 1. Okay, last 2. One of them is y equals e to the x. We talked about base e a little bit last year. We'll talk about it more this year. And this is really just a basic example of an exponential function. The base is just a cooler number than like 2 or 4 or something like that. But it is, if you take a number and you raise it to a power, what's going to happen is you raise it to a higher and higher and higher power. It's going to get bigger and bigger and bigger and bigger, so our graph is going to increase rapidly. If you raise a number to the 0 power, so if x equals 0, what do you get as an answer always?
0.
1. So this is going to cross the y-axis at 1. And then what happens when you raise a number to a negative power? thirds.
Oh, it just gets really small.
It gets really small, yeah, because for example, if I go 2 to the negative third, what I can do with that negative exponent is rewrite it as 1 over 2 to the positive third.
No fraction.
So now my exponent is on the bottom, and so like Gabe said, my number is going to get really, really small. Because this number on the bottom is going to get bigger and bigger and bigger, so 1 over that is going to get smaller and smaller and smaller, okay? So that guy looks like that. The number e is an irrational number like pi that shows up in a variety of applications. The symbols e and pi were both brought into popular use by the great Swiss mathematician Leonard Euler, who used it on a Twitter post, and it went viral.
On a Twitter post? That was a lie.
No,
You just made
that
that.
Tweet back in 1707.
Tweeted back in 1707. Just came up with a new number, calling it pi. And then all of a sudden, it was out. It went viral.
Yeah, for a second.
I did have you for a second. Thank you for that, because that's the only reason why I come back to work every year.
See you there next year.
Oh, a little chat with my wife. You're not pulling your weight, honey. I think I'm done. It's up to you now. All right, last one is y equals natural log of x. I don't know if you remember, but natural log is the inverse of, I'll give you a hint, the answer is e. Nice, it's the inverse of e. Natural log and e are inverse functions of each other. You guys are such great students. Yeah, we did natural logs last year.
And no logs.
That graph looks a lot like the square root function. Looks something like that. And this does have a fascinating, interesting fact. I love this. It's my favorite interesting fact. You ready?
Yeah.
This function increases very slowly. If the x-axis and y-axis were both scaled with unit length 1 inch, so if I took this and physically made this one be 1 inch, and then the next, 2 would be an inch, and then that's an inch, and then I kept going an inch this way, that's crossing over. You get it?
Yeah.
Okay. You would have to travel more than 2.5 miles along the curve just to get a foot above the x-axis. So we'd have to go 2.5 miles that way before we got to 12 on the y-axis. Is that amazing fruit or what?
It's pretty delicious.
It is, isn't it?
Alright,
Okay, you got 10 minutes.
No.
So that's just enough time to give you some homework.
No, really?
Okay, what page 3 to 3?
Take a look.
105, do I have that one?
I thought you were my paper supplier.
Yeah, man.
I'm addicted.
Some of these things are going to have some concepts in there like domain and range and even and odd and symmetry and stuff that you might have to shake out some spider webs to come up with those, but we'll discuss them tomorrow. It'll be a great way to review those concepts.